Okay. Hi everyone. Hi everyone. Welcome to the Single Cell and Spatial Exploration Club this week. It's me. I'm Hazel again, and today again with me we have Julie. Oh, hello, Julie. So we are
Hello.
by yeah, yeah. We are both biologists here at Bioturing, and for this week we will explore the heterogeneity of the tumor microenvironment in head and neck cancer. So actually, this is the following session with the previous week session where we also work with the head and neck cancer, where we find out some characteristics of the uh, you know, the transition of the cells in the cancer. And before we begin, I want to give you guys a little recap of what we have presented last week. So, Julie, can you please give us a little bit of recap here? Yeah.
Yeah, so last week we explored some single cell and spatial data of head and neck squamous cell carcinoma, and we found this particular subset of epithelial cells that was low in CDH1 expression and also high in MAL2 expression. And within this subset of epithelial cells, we found that they're linked to this epithelial mesenchymal transition or EMT pathway, which plays a huge role in metastasis. And so when we try to see this pattern again in our spatial data, we look at two different sites of the tumor, one at the invasive front where we can see the tumor interacting with host cells. We can see some of the pathways upregulated in the tumor are EMT related, which means that this is the site of metastasis. And this is in contrast to the inner site of the tumor where we see pathways more associated with tumor growth, but not necessarily metastasis.
Yeah, sure. So last week we actually, we introduce you guys to like a process we call epithelial mesenchymal transition, which is very famous and very crucial in head and neck squamous cell carcinoma. And then, yes, actually just show you guys that we work with both single cell and also spatial data, where we actually like introduce the characteristics of EMT. So in today's section, we will actually dive further into what type of EMT that we can see during the cancer, and we also dive into the cell type composition of the tumor microenvironment. So as you can see in the agenda right here, we divide this talk today into two parts. The first part is where we will explore the heterogeneity of the tumor microenvironment in head and neck cancer, where we will explore two different populations. First, of non-malignant cells, and in this population, we will see like the heterogeneous in composition, but quite functionally homogeneous. And then with the malignant cells, we see a quite different situation where we'll show you in a little. And then in this malignant cells population, we see a thing we call the partial epithelial mesenchymal transition, or partial EMT in head and neck cancer. And then in the second part of this session, we will show you more about what is partial EMT, and then at what, at what stage of the cancer that we can see the PEMT. Okay. Then now we will, go directly into our first part. That's to explore the heterogeneity of tumor microenvironment in head and neck cancer. And then here now, Julie will show you guys the example data set that we are going to use today.
Yeah, so I just want to explain a little why we're studying this tumor microenvironment. So studying this is quite crucial for understanding cancer progression, for treatment resistance, and also metastasis as well. And so the diverse composition of malignant and non-malignant cells in the tumor microenvironment influences this tumor behavior, including immune evasion and therapeutic response as well. And so unveiling these complexities enables the identification of more patient-specific biomarkers and more novel therapeutic targets. And so additionally, understanding the functional commonalities across the heterogeneous tumor microenvironments can help guide the development of more effective, more broad, and more applicable treatments to head and neck squamous cell carcinoma.
Yeah, sure.
Okay, so to introduce the data set, in this data set, the authors took samples from 18 patients and two sampling sites, each of which have, or total of which have 9 pathological stages. So you can see how we divided these samples into the two sampling sites at the primary tumor site and at the site of metastasis. And each of these stages here represents a pathological stage or a stage in the progression of the cancer. The authors also annotated the cells into malignant and non-malignant cells. And so in this analysis, we are going to characterize what makes these cells malignant and what makes them non-malignant.
Well, in here, I can see that we have the primary tumor site and also the site of metastasis. So if you already watched, the last week session, you may see that this primary tumor site is actually the inner part of the tumor, whereas the metastasis, the site of metastasis, is like the front end of the tumor, where the invasion of tumor cells actually happen. And then in here, we got the malignant and then non-malignant. So in this specific paper, Julie, how do you know how did the author define the malignant versus the non-malignant cells?
Yeah, so in the paper, the author defined malignant cells as those cells expressing a high copy number variation or CNV, whereas non-malignant, they don't express much very high CNV. And then additionally to that, they also gave a couple epithelial markers as well to identify the malignant cells because epithelial tissue is the primary origin of these malignant cells.
Yeah, sure. Okay. Now we can go directly into the composition of non-malignant cells. Okay.
Yeah, so characterizing non-malignant cells first. When we look at let me circle this for you guys. So when we look at this orange cluster here, these are our non-malignant cells. And then the authors annotated them into a bunch of these cell types here. We see B cells, T cells, some fibroblasts, and macrophage. Particularly, we see a larger proportion of fibroblasts here and T cells here, which is what we expect at the site of tumor because there's a lot of crosstalk between immune cells and between fibroblasts and macrophages.
Yes, I can see like a very diverse cell type composition within the immune cells population here. So can we take a deeper look into specific cell types and their proportion in, immune cell versus the fibroblast cells?
Yeah, so in this next slide here, we're going to subcluster our T cells in orange. And then when we take a look at the subcell types associated with that cluster, we see cell types such as regulatory T cells, CD4 positive T cells, and CD8 positive T cells.
Hmm, Okay, so that's about the immune landscape. Of course, most of the time we see T cells because they perform crosstalk with the fibroblasts. Okay, so how
Mhm.
about the composition of the fibroblast population here?
Yeah. So again, we're only going to be subclustering our fibroblast population. And then looking at the subcell types, we see populations of cancer-associated fibroblasts, intermediate cells, and myofibroblasts as well. So cancer-associated fibroblasts, of course, are really important or they play a key role in cancer progression, whereas myofibroblasts, they play more of a role in wound healing and very interestingly in EMT as well.
Yes. Yeah, I noticed that even these non-malignant cells, we still see a lot of CAF of cancer-associated fibroblasts. So, maybe along the way one day they will become the malignant. We don't know, but that's very interesting to know. But
Mhm.
in here, like in general, I can see like the tumor microenvironment for the non-malignant cells are very heterogeneous. So I suppose that it must happens in, all patients, like every patient has the similar heterogeneity.
Right. So if we zoom out again, let me help with the annotation here. So again, we're just looking at this orange cluster, our malignant cells. Sorry, excuse me. Okay, we're looking at our orange cells here.
Yes.
And
Okay.
then here again, these are our cell types here. And then when we color our cluster by the patient ID, we can see there's not much of a pattern, really. We see a pretty random distribution of our patients into each cluster. So this means that that all of these patients, they have this somewhat equal distribution of these cell types. So this may mean that these non-malignant cells may not necessarily be what's driving this cancer progression between these patients.
Yes, because basically based on the distribution of every patient here, I can see like we have many patients down here. And but
Mhm.
the the composition of each patient are quite similar to each other. So which is, reflecting the homogeneous behavior across different patients here. So I wonder whether we see the same pattern with malignant group.
So actually in our malignant cells, again, if we color by the patient, we can see a pretty good association for each cluster with each patient ID. So since these malignant cells are kind of clustered by the patient or by each patient, this suggests that there's high complexity and there's high heterogeneity from patient to patient in their malignant cells.
Yes, this is very interesting. It's like in contrast to the non-malignant cell where the clusters actually form based on the cell type. In here, you see the clusters are formed based on the patient ID. Is that correct here?
Yeah, that's right. That's right.
So yeah, okay. So beside this heterogeneity here, what else do we have for this?
Yeah, so here, again, in the paper, the authors also provided a list of epithelial cell markers as well. And when we query for these epithelial cell markers, we can see that their expression quite highly aligns with our malignant cell group here in blue.
Yes.
So this tells us that our malignant cell cluster may be highly upregulated in epithelial cells.
Yes, I think that's quite obvious because we all know that the epithelial cell is the main source for the tumor, for the malignant cells. Yeah.
Mhm, mhm.
Okay. Okay. So in here, okay. Yeah.
Okay, so I just want to kind of bring this back to what we found in our last talk. So again, I remember that we found that this subset of epithelial cells is linked to epithelial mesenchymal transition. And so we kind of want to see whether we see these EMT pathways within this data set as well. Okay, so here, when I query for a couple important genes important to the epithelial mesenchymal transition, for example, our CDH1 and our MAL2 gene, and then we have VIM and HIF1A, which are markers for EMT. We have SNAI1, 2, TWIST1 and 2, and ZEB1 and 2, which are all transcription factors that drive EMT. And then we also have TGF beta I, which is an inducer of TGF beta. And then we have KRT14, which is a marker for epithelial cells. And so
Mhm.
we look at the expression across all of these genes in different patients, and we see that the expression is quite heterogeneous. There's no like overall pattern that we see. So this just kind of confirms that we see pretty heterogeneous expression pattern between each patient.
Okay. So like in here, basically what we are doing here is like we try to perform the gene expression analysis across like many of the EMT macro genes, and then we see very similar pattern between, when you compare based on the sampling regions and also based on the different patients, we always see the presence of epithelial mesenchymal transition or EMT. However,
Mhm.
what make what come why do we call it partial epithelial mesenchymal transition, but not like a full or whatever that?
Yeah, so let me go deeper into exactly the expression levels that we're looking at here. Okay, so again, we do see an expression of these EMT markers VIM and HIF1 alpha. However, we still have a very, very strong expression of KRT14, which is our marker for epithelial cells, which means that both in the primary tumor site and the site of metastasis, these are still epithelial cells that we're looking at, and they might not be transitioning over to that mesenchymal state yet. However, we believe that this may be a partial transition because we do see minimum expression of these transcription factors which drive EMT are ZEB1 and 2, TWIST1 and 2, and SNAI1 and 2. Okay. And then also, building off of that, we also see high expression of TGF-bI, which suggests an increase in TGF-beta, which promotes EMT as well.
As we highlighted here, basically what we see is that even in the site of metastasis or in the primary tumor site, we still see a lot of epithelial, which explain the name partial epithelial mesenchymal transition. Is as I understand, it means like in this EMT position, not all epithelial cells are converted into mesenchymal, but just half of them, like part of them, are converted, and therefore what we call partial. And so, yeah, and so I expect that this partial process maybe occur during the early stage of the disease. Is that right?
Yeah, that's right. Right, and so building off of that, we can say that partial EMT can still be involved in metastasis. And if we do some quick literature search, we find this one particular paper, excuse me, in which the authors found that they find that partial but not full EMT can still contribute to metastasis, and that full EMT can contribute to chemo resistance here.
Yeah, that's interesting. Like beside the partial EMT, now we also know that the full EMT, beside promoting metastasis, it also contribute to the chemo resistance. So it's harder to cure the disease as the patient develop full EMT. Yeah. Okay. So yes, the next part of this talk would be like where we explain further or explore further into the partial EMT, and then we will find out the presence of partial EMT along the pathological development in head and neck cancer. So basically, the question is, when this partial EMT occur during the head and neck cancer development?
Yeah, so one way we can find that out is by using the pseudotime feature on bbrowser X. So this lets us look at how throughout the development of the progression of cancer, do we see any increase or decrease in our genes that are associated with partial EMT or EMT? So switching over, I'm just going to demo what the pseudotime looks like on bbrowser X. So here in our data set, I've already clustered together our malignant cells only. And when I click on the pseudotime feature, I can choose the principal graph.
Oh,
Let me go back.
as Julie is demoing the feature, I think if any of you here are already biotrain users, please let us know if you have any difficulties when you're using pseudotime feature for your analysis on biotrain, and also if you're not biotrain users, let us know if you have any difficulties in pseudotime analysis in general. Okay.
Yeah. Yeah, so if I want to look at the graph by the stages of the cancer progression, pathologic stage.
Okay.
So let me explain a little bit about what these annotations mean. So we have two different annotations, T and N. The T refers to the size of the tumor, whereas the larger the T, the larger the tumor. And then the N refers to the stage of metastasis. So as we get further along into the cancer progression, it will metastasize more and more into more lymph nodes. Right. And so we associate the early stage of cancer with this T1 and 0 stage.
Okay.
So given that, we click the pseudotime feature, we want to generate our principal graph based on that knowledge of the pathological stage and see how the gene expression changes between these stages. Okay, and once we generate this principal graph, here it's asking us to choose the root cell. So generally we want to choose the root cell at what we know is the early stage of cancer. So I'm going to highlight the early stage of cancer here. It'll highlight our blue cells. Let me turn the opacity up on the blue cells. Turn this down. Okay, and generally we want to choose a root cell within this cluster. So I can choose this one here, Centroid 52. And then when I click run, let me go back to the results page.
Yes, okay. So
Okay.
this time analysis is very, very convenient to do because we already has the actual stage in hand. Okay.
Yeah, exactly. So in the results page, it generates 3 graphs for us. We have the trajectory inference graph here. As you can see, if we chose this little cluster here, this is cell state 0, and then it defines a new cell state as the gene expression of these clusters of cells proximal to these other clusters of cells changes. So typically we have a different cell state at each branching point here. And then we can summarize this data here in this graph format. So again, if we start at cell state 0 and at pseudo time 0, you can see how we're starting from the early stages of cancer. And then throughout the pseudo time, we're progressing through the cell state and through the stages of cancer as well. And then finally, in this last, go ahead.
No. I think it's quite interesting when we have like a little, little pink color. Like
Yeah, exactly.
okay.
And so, right. And so in this last stage of in this last graph, we see this is just looking at the distribution of the cell state here. And so as the color changes, the algorithm will define these different changes in color as a new cell state. Okay. And so given that, we can also superimpose that trajectory inference on top of our tumor sites as well. And so when we start from the primary tumor site, as we get further along into the cell states, it kind of transforms into the site of metastases as we get farther and farther out into these branches.
Okay, so like the process start from the primary tumor site and then
Yeah, from cell state 0 right here.
okay. Yes, I got that. Hey, yeah, cool.
Mhm.
Okay.
Okay, and so given that we want to see how our gene expression changes across these different cell states and across our different stages of cancer. So again, our EMT markers and EMT drivers, SNAI2, VIM, and TGFBI are all present in the primary tumor site and mostly within the kind of the early stages of cancer, of the cancer progression, especially VIM here. So if we go through stage 1, 2, and then up here, it's still kind of an early stage of the cancer, but not quite in the site of metastasis yet. However, we do see a decrease in our KRT14, our epithelial cell marker, as we progress into metastasis. And so this kind of verifies that as we get into metastasis, we're seeing a transition from epithelial cells to a different kind of cell state.
Yes, great. Like in here, we see a lot of, EMT marker genes expression, and we not only see, the time where EMT occurs, but we also see where does it occur, which is in the primary tumor site in the early phase of the disease, not like in the later phase and not again in the metastasis. Okay, yeah, great.
Mhm. Okay. And so that concludes our analysis of this data set for today. To summarize, we found that the tumor microenvironment in head and neck squamous cell carcinoma exhibits high heterogeneity while still maintaining a global dynamic. When we explored two different populations of cells, non-malignant and malignant, we found that the non-malignant population was highly heterogeneous in composition, but it wasn't necessarily the driving factor behind cancer progression because we still see a pretty equal or random distribution of these non-malignant cells across all of these different patients. However, in the malignant population, it's highly heterogeneous from patient to patient. It's driven primarily by patient-specific factors. And this partial EMT characteristic is linked to metastasis in head and neck squamous cell carcinoma, where partial EMT is initiated at the early stages of the cancer progression and may diminish following metastasis.
Yes, thank you, Julie. It's a very informative summary. And yes, that's all for the content of today. Now we can move on to the Q&A section. Please let us know if you have any question. And also, because, today we explore the single-cell RNA-seq dataset on head and neck cancer using B-Browser. So this is our single-cell RNA-seq analysis platform. Here we give you a little survey that your comment is very important for us to improve our platform. Please let us know if which steps during your single-cell RNA-seq data analysis are the most difficult for you, and then what should we focus on improving, and then also and then what else can we done to resolve the bottleneck of your analysis, and among the features that you have used in B-Browser, which one do you use the most? Or like, how could we optimize the features to enhance your experiment? And then it's like a news for you that we are planning to implement multi-model analysis for B-Browser, like the POTUP6, like ATAC6, or even more. So like, what type of data would you like to see integrated in our platform? Please let us know. We will make it happen. And also, what other types of analysis features that you would like to have? Please let us know as well. So yeah, now we wait for a little bit so that you can fill in the survey and also give us any questions that you may have. Please let us know. Yeah. Okay. Okay. Yes, last question here. Okay. And yes, last but not least, if you have more questions for us, and if you want us to show you more on B-Browser, you can always book a meeting with us. Yeah. Thank you so much. Okay, so I think that's it for today. See you next week. Bye. Bye.
Thank you, everyone. Thank you all
Bye.
for joining.
Yes, thank you for your time.
Bye now.